Now we're going to talk about the unit tangent vector. So this definition says, let C be a curve defined by a vector-valued function r, and assume that r prime t exists when t is equal to t naught. A tangent vector v at t equals t naught is any vector such that when the tail of the vector is placed at a point r t naught on the graph, vector v is a tangent to the curve C. Vector r prime t is an example of a tangent vector at point t equals t naught. Furthermore, assume that r prime t is not the zero vector. The principal unit tangent vector at t is defined to be t equaling r prime t over the magnitude of r prime t, provided that the magnitude of r prime t is not zero. So this tangent vector we use for different calculations later on in the class. Right now, we're just going to try to find this tangent vector. So the first step here, we got a problem down below here. It says given RT being sine t cos t, find cap t, which is my unit tangent vector. So the first thing we need to do here is find r prime t. So in finding r prime t, it's just the derivative. And again, it's component-wise derivatives, so this is very quick and very simple if you know your derivatives. So sine of t, the derivative of that is cos of t. And the derivative of cos of t is going to be negative sine of t. Okay, now that we found the derivative, we have to find the magnitude of the derivative as well for the formula. So now I'm going to take this and find the magnitude. So it's the cos of t and then negative sine of t. And then that means we're going to get the square root of cos squared t plus negative sine of t squared. Okay. So then this equals here the integral of cosine squared t plus sine squared t. And we know cosine squared t plus sine squared t equals 1. So this is really the square root of 1, so it actually equals 1. So the magnitude of our vectors are 1. Okay, so that means when I find t, now again, t is r prime t over the magnitude of r prime t. So this means I'm going to get cos of t, comma, negative sine of t over 1. And I didn't have to write that, but I wanted to show you the formula in its fullest. So the answer here is going to be cos of t, comma, negative sine of t. Now I want to do one more thing with this. I wanted to pick a t naught, some value there, and I just wanted to show you how this vector actually looks geometrically. Actually on the graph of sine of t, cos of t, the RT that we have here. So now graphing RT, if I pick 0 for t, the first value then is going to be 0, 1. So that vector is going to be 0, 1. And I'm going to go up 1, 2, 3, 4, 5. I'm going to go up here for that first point. So it's going to be up there. Now again, remember, this is a vector I'm talking about here, but I really just care about the point at the head of the vector. Okay, and then the next point then is going to be at pi halves. So then this is going to be 1, and that's going to be 0. So it's going to be at 1, 0. So that's going to be here. So then the next one's going to be down here. And the last one's going to be over here. So we're really looking at a circle here of radius 1, which makes sense why our magnitudes then were actually 1. And notice our direction. Our direction is actually going, in this direction. I'll fix it. Okay, so now let's pick a point. Let's pick a t. We know we start here at this point. That's going to be our 0. That's what we plugged in first. So we can pick 0 if we choose. So we can do that. And let's calculate what that would be for our t. So t of 0. That's going to be the vector 1, 0. So that means if I just drew the vector would go out this way, 1. But notice what this set up here. It says when the tail of the vector is placed at RT naught on the graph, the vector v is tangent to the curve C. So when I take that tail and place it there, now this is my curve C here. I'm going to take a different color here. I'll do a blue. I'll call this blue. So when I take this 1, 0 and I put it there, that's going to be that vector, 1, 0. Because it's going to the right one and not up or down. And we can see that that's actually tangent to the curve. And that's what they were saying here. And that's why they call this a tangent vector. So I just wanted you to see how the geometry works here. It's pretty nice how this works out. So we're going to be dealing with this tangent vector for a lot of types of calculations. We're going to use it for outward flux. We're going to use it for circulation. So this is going to play a big role for us later on. And some other things too you'll see as they come up.